Good evening, everyone, and welcome to the Bangalore Theory Seminars. It's my pleasure to introduce the speaker for the day, Professor Sándor Fekete, who is the head of the Algorithms Division at TU Braunschweig. Professor Sándor did his PhD at the University of Waterloo, following it up with a postdoc at Stony Brook University and a habilitation at the University of Cologne. Before moving to Braunschweig, he also held a faculty position at TU Berlin. His research interests lie in geometry and optimization, but he also bridges the gap to applied problems in robotics. Today, we will hear from him about this intersection of theory and practice in some optimization problems. So without any further ado, I'd like to hand it over to you, Professor.
Yes, thank you. Is this on? No.
So the green light shows that it's on.
Now it's on, right? Good. Well, thank you all for coming here, and thank you all for having me here. And I would really like to thank my host, not just, the usual thing, thanks for inviting me and so on. This was actually a relatively short notice that made me realize that during an official visit to Mumbai, I had the opportunity to come by here. So this is my first time in Bangalore. I already enjoy it and love it, but also arranging this seminar talk. So just a quick look around. Who of you has worked as a researcher in algorithms in theoretical computer science? Okay. Anybody here who would consider themselves on the practical side? Okay. And who here, I was told that there are possibly some master's students who are aspiring to do one or both of these? Anybody here? Okay, don't be shy. So I like to interact with the audience, and what I'm presenting here, I very much invite you to interact with me. You can do this, of course, by asking questions, raising your hand, but also looking amused or puzzled or annoyed or something like this. You will see that I respond to these visual inputs. So if you have looked at this, you get a preview of what's up, and I promise there will be a bit more. And let's start with something from ancient history, at the time when people didn't really know what zero was. So we go back quite a while, 3,000 years ago. And of course, I come from Europe. Oh, this is a little mixed up here. I come from Europe, and so you recognize this is the Mediterranean. There was this really smart guy in Western Greece who was very much in demand. And he was called up to help some colleagues further east and solve that problem. And on his way back home, he traveled quite a bit involuntarily. And when you look at this, you see, I don't know how good your Greek is. I mean, this is sort of epic. You can read this?
Odyssey.
This is the Odyssey, precisely. Yeah, this is the beginning of the Odyssey. So this is Odysseus, who took 10 years to travel the Mediterranean. And you see, obviously, this is a suboptimal tour. He should have done much better. And so what I'm talking about is, of course, the traveling salesman problem. Everybody here knows the traveling salesman problem, I presume. So we know the traveling salesman problem as a prototypical optimization problem in a graph where we trying to find some optimal structure with some properties, in this case, a Hamiltonian cycle, or in other words, a closed round trip that visits every vertex precisely once of minimum length. And we know there's an exponential number of possible tours, n factorial. Finding the one best is not just finding a needle in the haystack, but we also know that this is an NP hard problem. Now, what does it mean when you have an NP hard problem? There's a few things you can do, and there are a lot of standard things that people here in this room have already been exposed to, even people who are never exposed to computer science, they have heard about these things. I'll show you a few of these later on in my talk when I'm talking about physicists who have learned some computer science. So now let's continue this, and this is more recent. This is actually very fresh.
Become the first to mine helium on the moon. Specifically, Specifically, the moon contains a rare form of the element known as helium-3. Tech companies want the helium-3 because it's needed to build quantum computers, which are way faster than our current computers. For instance, for the math problem, a salesperson must travel to 22 cities, visiting each city only once and returning to the first city in the most efficient route. A laptop computer would take about 1,000 years to figure it out, but a quantum computer could one day compute the solution in minutes. Totally worth fracking the moon.
I don't know if you recognize this this person. This is Stephen Colbert, a late night talk show host, probably the one most popular. And when this makes the evening talk show that traveling 22 cities takes 1,000 years, you're shaking your head, you know better.
This graph is on, there's a metric space, right?
Yeah.
So you could do better. Probably.
We can do better. And we can actually, so here's that thing again, 1,000 years. So here's the master plan. Collect 300 million, this is dollars. And fly to the moon. I mean, 300 million to fly to the moon. This was collecting some startup money and then probably getting more, right? You know how that business model works. And then you go and you harvest this helium-3. It's not so easy. On the moon, bring it back to Earth. Okay, that's another thing. And then you build these quantum computers. And at the end of it, that's the pinnacle. You compute this 22 city problem. But this was on a late night talk show, so it must be true. In fact, this was also in the Washington Post. Democracy dies in darkness, it says here. But yeah, what did they do for the math on this? They said, okay, well, 22 factorial is a certain number, and if you can compute the length of any permutation in a certain amount of time, there's something about the base frequency of your computer, and then you just do one per, and then you check, and then it takes 1,000 years. Here's 3 people who are skeptical about this. Maybe you recognize this this young student here, but this year is actually Bill Cook. I don't know who in this room has heard of Bill Cook. Bill Cook is an expert on practically solving traveling salesman problems. He's actually professor at University of Waterloo, recently retired, and 30 years ago, together with his colleagues, one of them is David Applegate this year, he was able to solve a 13,509 city problem, all the post offices in the US, to provable optimality on a computer 30 years ago. I mean, you look at Moore's law and so on and so on. But there's a bit more, right? So here, quantum computing, quantum computers, why are they developed? And why? This is actually a twist. It's not about they're so expensive. Is it worth it? They're so dangerous. They're going to destroy the internet, and all the security and all the cryptography will be broken. Why are we risking this? And then the answer here is we will be able to solve traveling salesman problems. That's totally worth it. Not just fracking the moon, but breaking the internet. And so here's a tweet by Bill Cook in response to this. Computing optimal TSP route on 22 points takes 1/200th of a second on my iMac. Now, a lot of this is just overhead of starting this thing, right? And that gets us to the question, what does it mean when a problem is hard? And what do we make of it? So I come from a theory background. I got my PhD from the University of Waterloo. And the usual thing that happens when you know a problem is hard, that's an excuse to do great theory. Because then you do approximation. Or maybe you look at special cases and say, if I have these extra properties, like you were saying, metric space that helps us, if it's a special type of graph we're traveling on, maybe you can reduce the possibilities and filter this out. And maybe if you do this on threes, maybe you can do this optimally, things like that. But even then, it doesn't mean just because the problem is hard that you have to stick to worst case asymptotic complexity. Because worst case is pessimistic and asymptotic is fatalistic. So in the long run, we're all going to be dead. In the long run, the sun will explode and the universe will die. Who knows what the complexity of our algorithms is by that time? So it's a lot more human to care about like what size of problems can we actually solve. And this is not in theory as in complexity, but complexity is really good. It gives you a good idea of growth, but the constants also matter. The constants, when you look at O notation, like where's the n0 where you start having this? What are the constants which you multiply, which are in this baked into this O of? And so I bring you here 3 different geometric optimization problems, which are all NP hard. And I'll show you that they're still extremely different. So that beyond asymptotic complexity, that there's some fundamental differences where if you look at practical computation, there's something we need to do. So we talked about this. And here is an instance not of 22, but of 200. 200, okay? So 22 factorial, according to the Washington Post, takes 1,000 years. 200 factorial is 10 to the 370. The universe will be long gone by that time. So we need, as you heard from the National Institute of Science and Technology, we need specialized computers. And so, in fact, I brought one of these specialized computers. It's called an iPhone. Maybe you've heard of these special computers. So this is actually a screen capture from my previous iPhone, which was an iPhone 12. So it's pretty much, but it's an iPhone app that you can download from the App Store. That's Bill Cook, who I pointed out to you a couple of pictures ago, built, which captures a lot of this mathematical expertise in solving these things. And I could do this here now, but of course I did a screen capture beforehand, so you get an experience. I'm going to press the button and solve this. This is a real-time screen capture. No funny tricks. If you want to see this, you can come up to me afterwards and we do this interactively and I'll show you how this works. So I'm going to press the button and we're done. 10 to the 370th, whatever, millennia. So this is provably optimal. This is only 200 points. So the question is, how large instances can you actually solve to provable optimality? Where do we have to start worrying about asymptotic complexity and approximation and so on? And I do approximation algorithms and theoretical approximation algorithms, but a lot of this is more about wisdom and philosophy and art and deep insights, and not because we need to do these things to avoid fracking the loop. So here's that what I mentioned, the 13,509 cities in the US. Here is that complexity. It sort of interferes with a slight number, so 10 to the 50,000. And they did this in 10 years of CPU time of 1996, 97. If you factor in Moore's law, that's a lot less than that. Oh, this was 98. Okay, so we can get to roughly 10 to the 4 many points to prove optimality in a reasonable time. Here's another. I give you a set of points in the plane, same thing. And now instead of minimizing the length of the simple polygon that you're getting, I want to minimize the enclosed area. Okay, very similar problem, very same set of feasible solutions. How fast can we search this? How fast can we optimize this? This was actually the topic of the first ever computational geometry challenge, which is about solving practical problems. Not proving theorems, but here's a set of benchmark instances. Find the best solutions you can in competition in limited time, like a few months, whatever. And the largest instances we can solve to provable optimality are about that order of magnitude. I will show you in a few moments where that difference comes from, but it's striking, right? I don't know if that's worth fracking the moon for, but it is a fundamental difference, not just from a theoretical point of view. From a theoretical point of view, in a certain way, this is even the easier problem. They're both NP hard, but for this one, we don't know if it's in NP because of Euclidean distances, and that's a long-standing problem. Coordinates, Euclidean distances. We know that this is an NP because area, this is much nicer to compute. Okay, I mean that's not such a big number compared to the 10 to the 50,000 possible solutions. Now here's another one. I give you again a set of points in the plane. Points in the plane. Can you at least see that? Sorry, I cannot rip this out. Maybe you. And I want, in this case, not a polygon. I want to triangulate the convex hull. So subdivide it into triangles, and I'll show you more about this as well. Subdivide it into triangles such that the total edge length is minimized. That is, again, an NP-hard problem. I'll show you more about this. I'll show you how this works. This was a long-standing open problem, the complexity of this. But we can do this to provable optimality for 100 million points. When you estimate how many triangulations you have for 100 million points, that is a large number. I mean, that's a ridiculously large number. And that is a paper, and I'll show you a few more things where that difference comes from, to give you some intuition. But just summarizing this, these are all hard problems, but they're fundamentally different. And if you just look at it with the eyes of asymptotic worst case complexity, they're equivalent. They're equivalent. I mean, that's what NP is about. That's what NP hardness is about. Yes, please.
So are there differences with respect to the input instance, or all the instances of that size?
So I need to answer this carefully. First of all, the input instances for all of these three problems are the same. In principle, it's a set of points in the plane described by their Euclidean coordinates. Now, when you get to problems of this size, of course, you need to be mindful, like, what instances are you looking at? So this is where we're getting to benchmark instances and like, what is a typical instance? And of course, we can argue about this. This is also where, as a theoretician, we want to be careful. So we're looking at worst case and we construct these hard instances and so on and so on. There's a bit more that can talk about. I hope I answered the first level of the question, and maybe we can come back to this later. Okay, let me talk about this. Minimum-area polygons, which is sort of the hardest of these. So here it is. Here's a set of points. Yes, please.
The previous slide, it relaxed the constraint to be not exact, but with some slack. Then do they perform similarly by?
So you mean when we say an approximately? Yeah. So you are okay with a suboptimal solution but close to optimal. Well, we can do this, and what it means is, so what I showed here. Let me just go back to the slide. For this, we can bring the gap to 0. Okay. Now, of course, what we can do is say like 1% is good. Okay. Then we can take this and push it further But you can imagine that the numbers, all of a sudden, because we allow 1%, we can't do it to 100 million points. There are some things, and there's this great area of approximation algorithms where you can deal a lot with this. And if you go to 1%, it's usually an epsilon, which is 0.01. But you still need to be mindful of the runtime. Because in the fine print of an approximation algorithm, even if it's a p-task, usually you get something like 1 over epsilon is in the exponent. And if you have, like, say, 1% and 1 over epsilon, that's 100. You have an exponent of 100. You're not going to get too far. You have a follow-up question? I see that.
We have practical algorithms that are able to take very huge numbers for the exact solution. How do the same, like, does the gap exist without having to go through the, let's say, we are not implementing the p-task itself, we are implementing a modified heuristic, which gives us probably efficient, probably approximate.
So I'm not completely sure. Let me try to answer it. And then I'd be happy I'm around so we can have more detailed discussion if I'm still not clear. So there's a difference between the theory side and the practice side. And on the practice side, there's sort of reasonable runtime where you say, I can do this in seconds, minutes, hours, days, potentially years. And on the theoretical side, there's this concept of the polynomial runtime. But when you look at the polynomial runtime, you say polynomial is good, even if they to something. And then we'd have to be able to push this further, we'd have to look at, like, what are the constants and how does it scale? We can do this. And maybe let me continue a bit more about the problem descriptions and then see if we still have problems, questions, we can talk one-on-one after this. All right, I was here in this. Here's a set of grid points. And I want to find a simple polygon with this fat vertex set. This is unit distance and all this. And so here's such a simple polygon. And as I was saying, the objective is to minimize the perimeter. That's the traveling salesman problem. So instead, we want to minimize the area here. And I can ask, like, is this minimum possible area? And is there an argument for this? I don't know how much you have dabbled in discrete geometry, because there's some very beautiful theorems in discrete geometry that tell you something about geometric measures. In particular, there's this Fick's theorem. You have heard of this? Who has also heard of Fick's theorem? Who else? Anybody else? 1, 2, 3. Okay. So for the benefit of the rest here, Fick's theorem says the following. If you have a grid polygon, all the vertices are grid points, and you want to compute the area, you can do this by counting grid points. You count the number of grid points which are on the perimeter, take that number divided by 2. You count the number of points which are interior, 1, 2, 3, 4, 5, 6. And you count this. This is 6, 1, 2, 3, 4, 7, 8, 9, 10, 11. Divide this by 2. That's 5.5. 5.5 plus 6 is 11.5. You subtract 1, that's 10.5. That is the area of this polygon. It's a really beautiful theorem, and I was very proud when I discovered it as a PhD student, and I was sad when I discovered this had a name and it was old and somebody had to come up with it, but I was still happy that I figured it out. So the way to prove it is you can just subdivide this into triangles, you triangulate it, and then you can convince yourself that the number of triangles corresponds to the number of these grid points, and every of these triangles has an area of 1/2. Which also means that this is in NP, because it's got to be a multiple of 1/2, and you can verify it looking at the grid points. So is this optimal? Well, what's the smallest number you can have? You look at the grid points on the boundary, and because these fat grid points must be on the boundary, you cannot avoid them. And well, do we have any points interior and grid points? No, we don't have. Do we have any other points on the boundary that are grid points which are not? Yeah, we do. Here's this one point, right? So that one point is in the way. If we had managed to avoid capturing this, we know there's a lower bound, which is n over 2 minus 1, which is the points on the boundary which we must have on the boundary because they are vertices of a polygon. So can we avoid capturing this point? Well, that's tricky. This one. So in a sense, we are within 1/2 of the optimum, but we don't know if this is the optimum. We have a lower bound as well. So now let me just change the point set. Abracadabra. And I use this point. So compared to the previous one, I just basically added this grid point. All right. As soon as I do this, you can check there's no extra grid points. Okay? Nothing extra. So this is the optimum. But the way to get rid of this point here was by capturing this point from here, which I could only do after adding a point here. Which means that when you look at distances, like perimeter, even when there's a lot of possible connections, this is localized. And an optimal tool will not, the optimal traveling salesman tool will not do these things. That's obviously stupid. You should not do this. But area works very non-locally because you have this almost degenerate triple that allows you to go all the way across and snatch this point. And that's really at the heart of why this problem is so agonizingly difficult. You cannot filter so well. You cannot say like, that's obviously stupid. No, it's obviously smart. So the structure of these polygons is much more all over the place than for traveling salesmen. And in fact, here, if somebody going to Waterloo soon, this was my PhD thesis from Waterloo, Geometry and the Traveling Salesman Problem, where I turned into some journal paper here where I showed that this problem is NP-complete. Ironically, it was really hard to show that this problem is NP-complete because the problem is so agonizingly difficult. It just does all these crazy things and everything is just connected to everything. To isolate the logic that you can encode and to make sure that nothing else interferes took me a long time. So yeah, there was some stuff here. And so here's an overview of the construction where you like do this and then you go here and you do this and so on and so on. That is somewhat related to some Hamiltonicity. So you have a problem for which it was difficult to show hardness because the problem is so difficult. And that gives you an idea of why we're having trouble solving this optimum. So even if we can really expand our range from 30 factorial to 50 factorial, that's still tiny. There's an approximation algorithm, in fact, algorithm, by the way, for the maximization area. And you know Waterloo is in Canada, so that's sort of appropriate. That gives you a factor 2 approximation, which is still for the maximization problem. We do not have any approximation algorithm for the minimization now. Nothing, no. It may be completely hard, probably is. One of the difficulties is good bounds are really hard to come by. The only good bound we have is this pick lower bound. Yeah, so that was this, where we gave it as an optimal problem and so on. These instances, so yeah, we gave them some bigger instances and find good solutions. You don't have to prove that they're optimal. Just find the best you can in competition to other people around the world. And yeah, this was running for a couple of 3 months actually. And some outcomes and some more outcomes. This is an ongoing project. We just finished the 8th competition, and some of this funding is good. There's something about instances and creating good benchmark instances is a challenge, because if you just take random instances, they can actually be easy. So I guess everybody here, or most people here, have heard of bin packing. So if I give you a bunch of numbers and I want to group them into a bunch of numbers between 0 and 1, and I want to group them into groups that such that the sum never exceed 1, small group as possible. Okay, we know that's a hard problem. But now suppose we want to generate benchmarks. And somebody says, okay, let's just draw some random numbers. And so we're going to produce a set of random numbers between 0 and 1. Uniformly at random. And they say, hey, let's see what we can solve. And you realize that when you think about this for a moment, it makes perfect sense. The bigger the instances get, the easier they get, because for every x between 0 and 1, you're likely to have a 1 minus x between 0 and 1. And the little deviation between uniform distribution between 0 and 1 becomes, relatively speaking, smaller and smaller and smaller. So you can really fool yourself. And if you're not careful, be fooled by others who say, like, yeah, we solved these big instances. So you need to be mindful and honest about this, which is why for Traveling Salesman, there's this TSP lib, set of benchmark instances, which come from different sources, and they usually have a structure. They're not uniform. They have some structure, and they turn out to be somewhat difficult. And when you look at these, they come from DLSI, and some of them come from pub crawling. So there's this instance of 50 pubs in Augsburg in Bavaria, or what is its smallest instance. So what we did is, take elimination maps of the world, use that as a distribution, random distribution, sample from this, and you get something which sort of corresponds to the geographic structure of geographic city instances. And that allows you to scale. You see, here's a bunch of these TSP instances, but yeah. And there's more. And there's more. Minimum-Weight Triangulation, okay? That was the other end, the bottommost. Here's a set of points. Triangulate them, such that the total weight is minimized. How hard is this? Well, that has a history as well. You may know this book, published in 1979, which was the first compendium. Some people call it the holy book of complexity theory on the theory of NP-hardness. And in this book, there's a lot of great stuff, a lot of descriptions, a lot of proofs as well, and a collection of problems. And in the end, you have a set of 12 open problems whose complexity in 1979 was unknown. And problem number 12 of 12 is actually this problem, minimum-weight triangulation. What's the complexity? So this is unknown. And this was actually solved 30 years later by Mulzer and Rothe. This is JACM, who showed that this is NP hard. They used a reduction where they embedded certain type of 3 satisfiability into this planar monotone 3 set. So you have some Boolean formula with variables and clauses. You embed this variable clause incidence graph and it's planar in a certain way where you can have them follow each other like this. And then you represent this whole thing by points in the plane. This is a schematic representation of this, and I'm going to show you more figures from this great paper, where you need to represent the logical bits and pieces, which are so-called gadgets, points here. These are actually points, such that you triangulate them just so, but you have more than one way to triangulate them, set variables, connect these variables, and you do a local choice between true or false, do it one way or the other way. And there's more. This is already figure 19. And there's more. And you see that gets nitty-gritty details here, numbers, you need to compare these. And there's more. And there's more. And there's more. And so on. And in the end, you can show this is NP-hard, which was amazing because it solved this really, really old problem. When it's printed in a book that had as the last open problem in this area, it's been around for a while before that. I mean, not more than since 1971 or so on, because, you know, Cook's theorem only came into the world then. But when you look into the details of this, you will realize that you take hundreds of thousands of points to represent and to encode a relatively trivial formula. So the example I gave you takes literally hundreds of thousands of points. And that's a lot of hard work. You can, with all this, you can represent any formula. So yeah, that's what an NP-hard proof is about. And this is another paper, hard in theory, easy in practice. And this is recent. This is basically current. And let me walk you through a few details of what we're doing here. You already know the punchline, the spoiler. We can solve instances up to 100 million points. Benchmark instances to 100 million points to prove optimality. Square roots, notwithstanding. No rounding, no rational numbers. Even if it's square roots, we can still do it. We need to be mindful of our accuracy and so on and so on. And again, like n squared runtime is not enough. 10 to the 8 squared, 10 to the 16. No. And so this whole thing works. We have a couple of geometric insights, filters, local optimality properties, which were known before. And then we can tie this whole things together and then do more implementation, algorithm engineering, and so on. Just because you think of something doesn't mean it's practical, it doesn't mean it works. And just because in worst case complexity, we know this is NP-hard, so yeah, in the worst case asymptotic complexity, this may blow up in our faces, but this is way beyond what we know. So here's one of those filters. There's some local property. If you have this diamond shape and if you have this edge, then one of those triangles must be empty. Because otherwise you could take this out and do this and you'd be better. There's a lot of fine print to proving this. I mean, there's a non-trivial number here. So it takes a proof, but it's a local optimality property. Which means if you have a lot of points there, you can throw away a lot of these if you have both of these non-empty. You don't have to worry about this. And this is about data structures to make use of this filter. And more and more and more. So there's data structures, and I mean, we all know and love data structures with algorithms. In practical use, you need them just because n squared is too slow. And then there's this and dynamic programming, blah, 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 blah. Second property, edges must be locally minimum. So this one here is locally minimum. We can use it. This one is not. And again, data structures, look at the set, filter them well and nice, make sure this works. Some figures for this and that. Exactness, so on and so on. And then we get into the nitty-gritty details, like these give us already so many edges that we're left with very little. So there's very little, like here, all this is the black stuff is given, and maybe there's something blue left. And in the blue, which is now localized and small, we can throw something more demanding at this to resolve. Dynamic programming, for instance, will solve convex holes. If that doesn't work, we can just use integer programming, solve this. And yeah, linear programming, with programming, experiments. So that's the graphic which this is all about. So you look at the number of points, and there's some different modes of filtering and doing computation, lower upper bounds, and so on and so on. And when you look at this, you see this is not logarithmic. This is linear. So you see this is linear. The runtime really is linear. Now something happens here, but it continues to be, well, you know, sort of linear. When you have a graph in practical situations and something like this happens, that's a sign memory usage. You're starting to run out of memory, and you do swapping, and you need to shuffle around data and so on. So yeah, your efficiency drops, but it's still linear, and we can just keep going here. And you see the amount of time that's like less than a couple of hours. Yeah, there's a few more things that we can do. And so the number of edges that we still need to do to look at, there's a few more things we can do. And this and this and this. And this and this. Oh, this is another more recent paper. Waving my hands over this. What is the timing that I'm supposed to?
18.
I still have 18 minutes. Good.
20.
Yeah. So can you do some similar things with different kinds of optimization problem? In this case, it's a triangulation where you're not minimizing the total length, but you're minimizing the maximum detour. Detour is defined as the ratio between the actual path in the triangulation versus a straight line connection. So this was last year's sausage, and that. So this is Philip. At least that's what he looks like when he's clean shaven, and this is Michael. Both extremely brilliant guys, and yeah, there's this. And let me just skip over this because we can do similar things, and there's some things we can do here, and let's just skip to this one. This is actually making progress on the theoretical side as well. Because one question you can ask yourself on the very theoretical side, not just how big instances can we solve, but what is the worst case dilation you can have for a set of points? That's a very geometric question. And you could convince yourself that if I give you a unit square and ask you to triangulate it, you have the choice to take this diagonal, that diagonal. And if you put in one, then you cannot put in the other, which means you need to make a detour, and that's a square root of 2, obviously, dilation, right? So is that the worst that can happen? Well, this figure here shows you that's not true. And this figure here shows you what happens if you look at a larger regular n-gon. So Wolfgang Mulzer was among many other people, among many other accomplishments, lead author on this triangulation proof that I showed you, the JACN paper, in his master's thesis, got about to here. That's sort of a list for 21 points, showing that, yeah, this is more than square root of 2. And this here is the worst case example for, so this is the optimal triangulation, the best dilation you can get for a regular, I forget, it was, I think it was 84 gone, which is that. And when you look at this, this is something you would never think of. I mean, you'd say like, yeah, there must gotta be some symmetry, let's do the math here and so on. Euclidean distances. And proving that this is the best, I would dare to say that you would never do this like with pen and paper, which also means you would never get some idea of what these things look like. So you would not even get to a good hypothesis as a human, which means that even if you don't care about all these things about how big instances can we solve, and you cannot ask ChatGPT to do this. You can't, because there's a lot of interface between theory and practice to get these kind of insights, right? And when you look at this, oh, that's actually this dotted line here is the upper bound that's known. So you see that we get to the upper bound is 1.4482, and now we have a lower bound of 1.4411. Very tight. Is that the worst? Well, you can imagine that maybe this will continue to grow and so on and so on. So be careful what you conjecture here. And be careful giving this problem to your questions. Okay, let me play this for you because this is fresh from last week. Freshly submitted to Sausage Media. And there's another couple of really great students of mine in Czechman mostly did this video. It also shows you what amazing things you can do now with the right tools to create videos.
We consider the problem of tracking a potentially large collection of moving objects, a fundamental problem with a long history and many important applications. In air traffic control, a typical scenario involves a number of stationary control centers, which are equipped with powerful tracking devices such as long-range radar, without much regard for the power consumption of tracking devices. With rapidly increasing number and ubiquity of small, lightweight drones, this type of air traffic control needs further development, such as the use of less powerful tracking stations. How should we adjust each sensor's radius over time to keep all objects covered while minimizing power consumption? Formally, we are given a set of moving objects, each following their own trajectory. We are also given a set of stationary tracking locations with adjustable sensor range. The challenge is to cover the moving objects with optimized power consumption that is proportional to the area of the disks. We assign radii to the stations, ensuring that every object is covered. The static problem is known as the disk covering problem and known to be NP-hard. By enumerating all possible assignments of objects to stations, we can solve the static version optimally using a set cover integer programming formulation. We developed an algorithm that can extend any feasible static solution to a dynamic one. In order to maintain feasibility, we identify event points at which the so-called supporting point of a disk changes. This allows us to maintain a feasible solution at all times. As one improvement, we identify event points at which it is cheaper to hand over an object from one station to another. This yields a cheaper solution across the full time interval. Now we can track the power consumption of our solution over time. We start with any feasible static solution and extend it to the full time interval using our algorithm. There are different objectives we can consider. One option could be to minimize the total power consumption over the whole time interval. However, for a large distributed network of sensors, it is also important to avoid undesired surges in power output. That is why we focus on minimizing the maximum total power consumption at any time. To derive lower bounds on this minimization problem, let's freeze time and look at a static instance at some arbitrary moment. For this snapshot, we can solve the static problem optimally with our integer program. That optimal solution is also a lower bound for that specific time. No solution dynamic or gives less power at that moment. Now back to the dynamic setting. Our overall objective value, and thus our current upper bound, is determined by the time with peak power consumption. At this peak time, we again solve the static snapshot with the integer program. This optimal static solution gives both a cheaper solution and a lower bound on how low the best possible peak can be. We can extend this solution forward and backward in time. Now we have two feasible solutions. We combine them by taking the lower envelope. This produces a new schedule with a lower peak. Then we repeat. We identify the time with the highest power consumption and solve the static instance using our integer program. This time, the integer program solution returns a better lower bound to our min-max problem. Again, we extend this solution in both time directions. Finally, we merge both solutions to obtain a coverage schedule whose peak power consumption is only slightly higher than the current lower bound. We can iterate this process until an optimal solution is found, or the remaining gap is sufficiently small. In our work, we show that, even though the problem is computationally hard, we can still solve it effectively in practice using one of three proposed algorithmic approaches. Indeed, we are able to solve instances with up to 500 moving objects and 25 stations to provable optimality in just seconds, while the scenarios themselves play out over minutes in the real world. Here we see an instance based on a TSP-lib point set. We randomly sample 25 points as centers and compute a maximum matching on the remaining points. Now we see an optimal solution for a TSP-lib instance, showcasing both the efficiency and the strength of our approach. For more details, see our full technical paper.
Yeah, so that's an upcoming ICRA paper in robotics. Okay, let me use a few more minutes that I have to trash quantum computing. I don't know if anybody here has invested in quantum computing morally or financially, scientifically. Anybody here? You have, okay. Before we go on with this, what do you have to lose?
Nothing.
Nothing, that's good. Okay. What is your relation to quantum computing?
I work on the patient side, so
Okay,
you can,
on the
Okay.
theory side,
yeah,
you prove theorems.
Yeah.
Okay, that will not go out of business, that's good. But you have not invested in a startup or something like that. Good.
don't do it,
Is that
don't do it.
good stuff? Yeah. Let me say a few words here. So this is actually, so I was quoting a US government institution. This is a German government institution that says basically with these computers, everything will become different and so on. And they say, oops, sorry, I was too quick. Spoiler. They say the important part is this is what distinguishes quantum computers from conventional computers that do this sequentially. They do everything in parallel, right? So 10 to the 22nd in parallel, and you're shaking your heads because we know that is not correct. It is not correct. And but it sells well. And so here is things you shouldn't know about quantum computing or quantum computers. This was written by an expert in quantum computing, and he says myth number 2. He's got a few. This is actually it's a little book of 100 40 something pages, I believe. PDF is available online. You can buy the printed version via Amazon, but you can look at this and try all solutions at once. Just wrong. Quantum computers will replace digital computers. Wrong. Break the internet. And this is an expert from quantum computing assessment. Now, I have had, for the last few years, a couple of multi-million euro projects looking at hard optimization problems and their interplay with quantum computing. The summary is this. First of all, on the classical side, we can solve a lot more, much further than people realize out there, outside of computer science. On the other hand, quantum computers will have a really, really hard time of catching up and may never be able to do this. So here's one. That's a linear program. And that's a paper from 3 years ago, but fast quantum subroutines for the simplex method. And this is a well-esteemed, very nice colleague as well, Giacomo Navicini, and he writes in this paper that he's able to use quantum computing to improve the worst case asymptotic complexity of the simplex algorithm by something. And I'm smiling because we all know, everybody who knows the simplex algorithm knows that in the worst case, yeah, kind of exponential runtime, but we still use it because the worst case is, the worst case. It's a really great algorithm and it hardly ever does something, and then you shake it a little and then it will still work. So if you were corner me in a dark corner, gunpoint, and say, tell me the worst case asymptotic complexity of the simplex algorithm, even though I graduated from CNO and wanted to do all this, my best bet to survive would probably be to fight you for the gun, because I mean, these kind of things I don't. It's nothing I think about. So we did with a big team of physicists and different mathematicians and of course algorithms people, computer science. We looked deeper into what this algorithm, how that would perform on benchmarks. Now, the problem is when you run a computer, you run it. You cannot run a quantum computer on many qubits because they don't exist. One question is, will they ever exist? That in part depends on, do we want them ever to exist and pay all this money to build large-scale quantum computers? And when you hear IBM in Zurich, 1,000 bits, 1,000 qubits, fine print, these are physical qubits, not logical qubits, because there's a lot of noise and you need noise cancellation and so on, error correction, all these sorts of things. So this was something currently revising, first version here on the archive. And there's a few things. How do we expect quantum algorithm to perform? We're making a lot of very, very benevolent assumptions on how the quantum computer, no error correction necessary, no noise, no decoherence times, no all that funky physics that plays against the quantum computer. We're nice to it. We said, yeah, okay, we give you this. Like, error is fine, noise, we don't care. We just let you run this and not worry about this. And then we do a lot of this. Actually, this was where our physics colleagues dug into this and said, like, yeah, let's analyze this and analyze expected times, right? So, more found this, and this, and this. And then we're doing some benchmarking. So here's what we did. This is simplex, right? So we can run a classical computer to run simplex on one of those. With that, we have an idea of the structure of this polytope and the structure of the solutions and so on and so on. And then we pretend the quantum algorithm would do it. And with all these lemmas, we have some estimates on how this takes, right? And then we can do these estimates and say, like, yeah, this is roughly how long this would take. And we have the benchmarks and some more benchmarks and so on and so on. And this is the first graphic, and this is the second one I want to show you. Now, when you think of doing quantum computing, it means you're using physical particles in a quantum state that is protected and preserved, that carries out some physical interaction. When you are doing one of these quantum gate operations, so it's a unitary matrix, and so you do a vector matrix multiplication with physical objects that represent this quantum state. When you want to estimate the runtime of this quantum computer, you need to understand how long it takes to carry out this Hadamard gate multiplication and whatever. And so there's been some measurements on a single isolated interaction between two physical qubits. Now, this is very, very benevolent. It's like saying, if we're sitting here opposite to each other, ready to go, how long does it take us to do a handshake? Now, if I were to shake all of your hands, this would be a lot longer. But I mean, a very benevolent estimate would be like, multiply the number of people by a single handshake like this. So the record for one of these handshakes, for one of his quantum operations, is about 10 to the minus 8. Isolate, no error correction, no ion shuttling, none of this other stuff. And now this is how fast this would have to be to make it comparable. And when you look at this, and this is for realistically sized benchmarks, which we can solve. These are realistic benchmarks which are used to benchmark practical simulations on classic computers. We need to speed this up by 10 orders of magnitude. That is physics. And okay, I didn't bring this. If you dig into the physics of this, there's some physics behind it. Why, if you use a classic computer and you have better chips, yeah, maybe eventually you can get 10 orders of magnitudes. The physics doesn't support this. So there's some platforms where to take one of these ions and to basically keep it in this quantum state, you have a rotating electromagnetic field, which is complicated. Somebody won some Nobel Prize in the 90s for this. And there's a frequency of this quadrupole field, and that frequency is somewhere in the single-digit megahertz, which means if you shove this around, it's going to slip off and lose its quantum state. So it's not going to happen. There's I'm running overtime, so we had something new. This is where's the date? I mean, this was last year. We actually have something for knapsack. For those of you who are interested in knapsack, I know there's some here. Where the idea is different. You don't use the quantum to do linear algebra, which is, matrix, a vector, these kind of things, which is very classical linear programming. You can do anything on a quantum computer, but it's not the nature of the quantum computer. Instead, if you can look at the feasible solutions of a knapsack problem, there's a way of filtering all the feasible solutions in relatively short time and put them into superposition. That has something to do with the nature of a polytope. For those of you, maybe the one person who was invested something scientific in quantum, I can talk about that and go much over time. So you put all the feasible solutions in superposition, and then you use some practically tuned Grover's algorithm to extract this. This is not a polynomial-time algorithm. This doesn't break NP-completeness, but it at least has some hope of being practical because the nature of the problem is related to the nature of how the quantum computer works. Because you're looking at this polytope that has certain geometric properties. And if you neglect that, if you neglect the geometry of your problem, then yeah, never mind this. Never mind this. Thank you, and that's it. Yeah, we actually hadn't looked at it from the point of view of the worst case. We have looked at it from the point of view, do we have any hope that this is practical? So we can look into the worst case as well. But basically what you always end up with is, and the majority of the papers do that, you save a square root by using Grover. And so instead of 2 to the n, you get 2 to the n over 2. Maybe times n if you want to evaluate the solution. Any other questions? Yes, please.
Quick question. So for the minimum weight triangulation problem, you mentioned these local optimality, right?
Right.
So do they also work for points that are that belong to your surface? Which,
So
the reason I ask is you said that your benchmark points come from these points on the globe.
that is a very, very hard question. For these points on the globe, we didn't consider that. So I mean, we do the projection and then we extract some of this. We haven't really worked on this like on a sphere, which is a natural question. You could, I mean, I was expecting you to ask, does this work in 3D, which is the standard question in computational geometry. And in 3D, I'm also not sure. We haven't tried this in 3D, whether and how these local properties work to our benefit and how well they work for our benefit.
I guess before going to 3D, I would be interested.
So I would venture a guess that if it's constant curvature like the sphere, then we still can do most of this. But if you have non-constant curvature, I don't know, hyperbolic, I don't know. But it's worthwhile thinking. You're just scratching your head. Okay. Be careful. Be careful. Did I answer your question from earlier? All right. Okay. Well done. Thank you all. Oh, thank you so much. I should do one more thing here. Thank you so much. I think I have. Do I have this here? No, I don't. Oh, my shame. I had a picture of my group, which I failed to put up. But I will not have. Thank you, everybody. Thank you. If you have more questions, I'm here.